Okay, so the setting we were studying is if we have points x1 through xn in Rp, right? We wanted to project them to low dimensions to do dimension reduction, right? And we wanted to project them to d dimensions. Right? And there were two ways of thinking about this. Either we wanted a basis, right? We wanted an orthonormal basis, normal basis of a d-dimensional subspace, right? Of course, with d ideally much smaller than p, such that there were two ways. Let's say v1 all the way to vd, right? All in Rp. And we thought about it in two ways, and we saw that this was equivalent, right? That we wanted xk to look as possible, as close as possible to, right, a shift, which we computed to be mu n, the right one, times the sum of bk, right, bk high, bi, right? Or what we wanted, and we wanted this approximation to be as good as possible, right? As close as possible. Or the other formulation was that we wanted the variance of the projection to be as large as possible, right? So the variance of the following points, V1 transpose X, K, V2 transpose XK, so on, all the way to VD transpose XK, right? Which would be the projection. Right? Take these points K from 1 to N, that the variance of these points is as large as possible. And we saw that this was equivalence, and that the basis, so the optimal V1 through Vn is given by the leading eigenvectors, right? So the eigenvectors corresponding to the leading eigenvalues of the covariance, right? Sigma n, right? Sigma n, the covariance of the points, covariance matrix of the points. Right? How did we? Let's just write out this equal to this again. S1 minus 1 sum from k from 1 to n of xk minus the average, xk minus the average. Okay. So now if you want to visualize your points in a computer screen, it's clear what to do, right? You pick d equals 2, you take the top two leading eigenvectors of sigma, and you draw the points in those coordinates. Right, if you have a nice program to see visualizations in 3D, maybe you do it for d equals 3. But there's many more applications for dimension reduction than just being able to visualize the data. Maybe you want to reduce the dimension for some kind of downstream analysis, or maybe you want to reduce the dimension because in high dimensions there's more noise and you want to ignore it. Right? This is also very useful. And so sometimes there's a very natural question of asking, what d should we take? Right? What is the right d? What is the right d? Right? Because in many applications, we're going to take d to be 10 or 20, right? The dimension maybe is 1,000,000, and we take d to be 50, right? The data still becomes much, much easier to understand, right? And we don't expect, that images of say, a human body in different positions can be nicely described by only two coordinates, right? So when we ask what is the right d, right? If we think in the sense of like how much variance is there in the data, right? If we take, lambda 1 bigger or equal than lambda 2 and so on, right? So if we take the eigenvalues, right, of the covariance matrix, right, lambda n, like the eigenvalues, right, of sigma n, right, then basically it's not hard to see that the portion of variance that's in the coordinate of vi, right, so the portion of variance here in vi, so in the coordinate vi is basically lambda I divided by the sum, right, by the trace. And so it makes a lot of sense, right? We take the bigger ones, they contain more variance of the data, right? Or they project better. If you think an error would be the sum of the other ones. Now, a natural thing to see is to try to look, so sort of a strategy, a decent strategy, is to look for an elbow, what's called the elbow method, or look for an elbow. Right? You can see this is not very mathematical, at least not for now. Right? And what I mean by this, maybe we take let's look at the following plot. Right? Where I'm going to take the biggest eigenvalue, the second one, third, fourth, fifth, and so on. Right? It's called sometimes a scree plot. And maybe we see lambda 1 is all the way here. Okay? And maybe lambda 2 is all the way here. And maybe lambda 3 is all the way here. Okay? And maybe lambda 4 then is here. Okay? And so on and so forth. Right? And then we draw this line, and we see this, right? And we see the elbow here. It's clearly, getting the first and the second eigenvalue gives us a lot of variance, and then after that, it gives very little, right? So we try to look for an elbow, and this is something that practitioners do different versions of this. But we want to try to understand, so we want to understand as mathematicians, like, what should we do, right? What is, how can we even define this? What D should we take? And how do we even understand what D should we take? Like, how do we formulate this properly? One way to formulate is to imagine that the data comes from some distribution. Right? So imagine the data comes from a distribution. So what if the data x1, xn comes from a distribution, right? Some distribution that may or may not have low-dimensional structure. What does this scree plot? What do the eigenvalues, do the e-values of sigma n look like? Right? Because if we understand this question, then we can sort of, when we see a scree plot, we can try to say, oh, if the data came from this distribution, it would look a bit like this, and this distribution had a certain dimensional structure, and so on. And so let's say, okay, let's try to make things simpler so that we can understand this a bit better, right? So that we can start doing some math around this. Okay, let's say that x1 through xn, right, in our P, comes from a Gaussian. So the RID and xk comes from a Gaussian, say with mean 0 and variance sigma. Okay, and so. Okay, so we have some variance sigma. And now, if sigma as a low-dimensional structure is like a low-rank matrix, or, has some eigenvalues much bigger, we would like to see this on the eigenvalues of sigma n, right? So we could now ask, what is the behavior, right? What is the behavior of sigma n, right? This is a very, makes a lot of sense, right? It's a very natural question. Now, okay, so let's see. So we know that the expected value of sigma n is equal to sigma, right? So even just by law of large numbers, we know that, right, sigma n, as n grows, should be going to sigma. Okay? And indeed, right, if n goes to infinity, as n goes to infinity, we expect this to happen. Okay, so this doesn't seem so interesting, right? And we're basically, the behavior of the eigenvalues of sigma n are just the behavior of the eigenvalues of sigma. Now, what is the problem? The problem is in high dimensions. So, in high dimensions, things may behave different, right? This may not be the case. What do I mean by the high dimensions? In many cases, in many, more modern data sets, we really don't expect that P is sort of small compared to n. We don't expect P fixed. P fixed n going to infinity is when we expect this behavior. But in many modern applications, we expect both n and P both going to infinity. Right? And this is what's called, this is what high dimensional statistics deals with. Statistics. It's all about understanding when n and p go to infinity. Okay, what happens then? Right? If both n and p go to infinity, it's not clear, right? It is not clear that, sigma n goes to sigma. right? It is not clear at all. And so we want to understand as n goes to infinity and p goes to infinity, what happens. Okay, and this is now a question of high dimensional probability. Now, what are we asking really? Right? We're asking about the behavior, spectral properties. Right? We're asking about spectral properties. Right? Things like eigenvalues, maybe eigenvectors of sigma n, right? Which is a random matrix. And now this would be, we're really trying to study the spectral properties of a matrix that's random. This is exactly the object of study of random matrix theory. So let's see an example. Okay, let's make things simpler, and let's say that we take the matrix X as the columns x1 through xn, right? And now we're going to take the matrix, instead of taking sigma n that has sort of this mu n and has n over n minus 1, I'm just going to take the following matrix, 1 over n xx transpose. Right, this is the same, right? Because mu n will go to 0 because the points are centered, and n over n minus 1 also goes to 1, so these objects should be the same, right, as n goes to infinity. So and studying this will be a bit simpler. So let's take an example. Let's look at the simplest possible example. Let's look when sigma is just identity. Right, so the points are just drawn from a completely isotropic Gaussian. There is no low-dimensional structure at all. Right? It's completely rotation invariant. Right? Rotation invariant. Right? Any rotation of the data looks just like itself, or of the generative process of the data. Therefore, there is no more meaningful directions or more meaningful subspace or anything like this. Okay, and now let's take p equals 500, and then equals 1,000. Okay, and now try it on the computer. You draw n Gaussians in dimension 500, isotropic Gaussians, standard Gaussians, and you compute the eigenvalues of the covariance matrix. Okay, and here's what you get. Right, I've done this already. Here's what you get. Okay, so look at this. Look at this plot. We expect, if n was going to infinity and p was fixed, the eigenvalues of the true covariance matrix, they're all equal to identity. The true covariance matrix is equal to identity, all the eigenvalues are equal to 1. So we would expect everything equal to 1, right? You see 1 over here. And instead, we see a huge spread of the eigenvalues, right? There's some that are quite small, quite close to 0. There's eigenvalues going all the way to 3, right? The largest ones go all the way to 3 even, almost. So if you had this data set, you would compute its covariance, and you'd see, there's eigenvalues here that are quite large. Maybe these eigenvectors have some meaning, and you would do principal components of those eigenvectors. And you'd be completely misled, right? Because in this generative process for the data, there is no special directions. All directions are the same, right? And so, as mathematicians, we want to understand what happened. How do we explain this distribution? When is it that, how much bigger does n need to be than p in order for this not to happen? If we get the data set in which a few of the eigenvalues are much bigger than what is in this distribution, then because we know what would have happened if there was no low-dimensional structure, then this means that maybe we can trust that there is some low-dimensional structure, right? Because now if we know that we're trying to look for elbows in here, right, this is sort of becomes the null hypothesis in a way, right? The place where there's no structure in the data. So if you see something more elbow, I'm not sure this is the word, but with more elbows than this, then maybe you can argue that there's some structure in the data, right? But in order for us to understand when there is structure in the data or not, we have to see what it would look like if there was no structure in the data. I think of it as a null hypothesis type of thing. Okay, and so how do we understand something like this? Like how do we, I have this red line here, right? Is because we can actually analytically predict what this curve is going to be. And as you see by the red line, it's a pretty good prediction, Right, and so how do we do this? Right, so this actually dates back to the work of Mashenko-Pasteur, right, already in the late 60s. So this is due to the work of Mashenko and Pasteur. Right, I believe in 67. And they worked out the limiting distribution of the eigenvalues of this random matrix. Okay? And the right way to normalize it is to have a parameter gamma, which is equal to p over n, to take p and n going to infinity, but have this fixed, right? Have this fixed. Right, so in that case, I just took gamma to be a half. And now in this limit, you can say, what does the histogram of the eigenvalues look like? Okay, so the sample, the distribution, the histogram, I should say, the histogram of the e-values of Sn will converge in the limit to a certain distribution, right? In a certain weak convergence sense that I'm not going to describe very carefully. Will converge to the following. So I'll write here the distribution. I mean, we won't prove this here, but I'll sort of tell you roughly how you could prove it. Okay, so this is, I'll just write out what the distribution is. I mean, what the distribution is not important. The important thing is that we can work it out. Right? And I mean, there's some things we're going to learn from it. Gamma minus. And indicator is only between gamma minus and gamma plus. Right? You saw that he had, a minimum and a maximum, this histogram. Okay, of lambda. Lambda. Right, d lambda. Okay, and what are these gamma minus and gamma plus? Right, so gamma minus is equal to 1 minus gamma squared. Gamma plus is equal to 1 plus gamma squared. Okay, and I'm taking here p smaller than n. If p is bigger than n, you can basically just, take the transpose of the matrix and study that instead. And there'll be some eigenvalues at 0, which correspond to, the rest of, because, right, the matrix will be low rank, but you can work it out based on this case. Okay. So how do we prove something like this? Okay. So one way to prove something like this, and we're not going to prove it here, right? But the point is that this can be worked out mathematically, right? But one way to try to prove things of this type is to try to work out what the moments are, right? So the point is that for any k, I mean, the idea is that for any k, right, if I take the expected value of the, right, so let me write it out. If I take the expected value of the trace, right, of 1 over n, xx transpose, my matrix Sn to the power k. Right, let's take this. I mean, how you would compute this is another question. We'll see that in a second. But basically, what are these? These are the sum of the kth power of the eigenvalues of Sn, right? And now I'm taking the mean of that, right, with respect to the randomness of Sn, and then I'm dividing by the number of eigenvalues. So in the limit, as n and p go to infinity, this should behave like, right? In the limit, this should behave like the pth moment, or the kth moment of this distribution above. And the point is that one can compute this, right? One can compute. And it's maybe not so surprising, right? Because if you start thinking about what the trace is, right, what you have here are polynomials of Gaussian random variables. So basically, you have to do a bit of combinatorics and use the moments of the Gaussians, and you can actually compute this. And if you do that, right, what you have, this is just the same as, right, the expected value of trace of Sn to the k, right? But what is this? This is 1 over p, right? Or let me move the expected value to the other side of 1 over p, the sum from, k from 1 to p of the kth eigenvalue of Sn. Right? And if the eigenvalues of Sn converge to the eigenvalues of that distribution, of the distribution f, then you would expect, right, as Sn goes to infinity and p goes to infinity, then this will converge, okay, let me go here to the line, will converge to the the integral, right, the kth moment of that distribution. Lambda k d f gamma lambda. Okay, and this is one way to prove it, right? So you use some, moments of polynomials of Gaussians and some combinatorics. With the combinatorics, you compute this for each k, right? Because of this argument, you expect that this corresponds to the kth moment of this Mashenko-Pestrel distribution. Because you know now the distribution, you just have to check that it indeed corresponds to the kth moment of this. If you didn't know, you now have to find a distribution whose kth moments correspond to this list that you're computing. Right? So this, for someone to do this the first time would be more work. But now that you know what to look for, you just have to show that the kth moments of this look like the kth moments or converge to the kth moments of this distribution. Right? And then you have to argue that if the moments converge, then you have enough regularity that you get weak convergence of these measures. Okay, but that's not what we're going to do today. Again, you can see this in in a book of any book of random matrix theory will have proofs of this style. What we want to study today is the spike model. Right? So using this machinery, you can see what it looks like for a distribution that has no low-dimensional structure. But what if the interesting question is, what if there is low-dimensional structure in the data? Right, this is sort of the key question, right? Do we actually see it? Let's make this a bit more interesting. Okay, let's take u, okay, some vector of norm 1, okay, vector, in our P, u norm 1. And let's say that in the direction of u, the data has a bit more variance. Okay, so the point is that the data, my data points are going to be drawn from a Gaussian, means 0, but the variance is going to be identity plus beta u transpose, where beta is some constant bigger than 0. Okay, so sort of there is variance 1 in all the dimensions, and in the direction of u, there's variance 1 plus beta, right? So there is variance 1 plus beta in the direction of u. Right? We can take the approach that sort of the data lives really in a one-dimensional subspace, in the subspace of U. This is really where the data belongs. Right? This is really the right structure, the right parameterization for the data. And this is sort of noise. Right? So we can think of this as noise, and maybe this is signal. Right? And if we think this way, then we might as well call beta some form of signal-to-noise ratio. Right? Now, a central question, right, becomes for which values of beta does PCA see this vector, right? For which values of beta does PCA see the signal, right? When is it that that PCA can actually see this stronger direction? So again, let's do the experiment. Okay. So remember the plot that we had before, right? So before we did a plot for p equals 500 and n equals 1,000, and it looked like this. So we see the largest eigenvalue is around 3. Okay. So if now we were to take beta bigger than 3, we really expect that we see an eigenvalue. When you take the eigenvalues now of the covariance, where we have the true covariance of the data looks like identity plus this beta u transpose. If beta is really, really large, right, we expect that we probably see something coming out. But let's take a beta that's a bit smaller than 3. Okay, in particular, let's take beta that is 1.5. Okay, so again, same model exactly as described here, but we take p, we take p equals 500, n equals 1,000, and beta equals 1.5. Okay, and now let's see what we get. Right, we draw the data from that covariance, and now we look at what it gives us. Right, we look at what's the sample covariance of the data. Okay? Here's what you get. There's something interesting going on. So if we were to do PCA to one dimension, we would get the right dimension. There is indeed a bigger eigenvalue here. Okay, we would have to argue that eigenvector correlates also with U. We'll do that in a second. But at least it sees that the data is sort of one-dimensional. There's something that pops out of the support. Also interesting is that the eigenvalue, right, the strength of the signal was 1.5. So it should have been buried somewhere over here, but somehow it gets pushed and it's now outside. Okay? And now if you do the experiment with like 0.5 or a much smaller beta, it looks just as if there was nothing. It looks exactly like it looked here. Okay? So if you don't do the experiment with, say, beta 0.5, you get exactly this. It's like there was no signal in the data. Right? But with 1.5, you get something. Right? The natural question is, can we understand this? Right? Can we mathematically understand for which values of beta do we see an eigenvalue popping out of the support? Right? This is now the interesting mathematical question. Right? For which values of beta can PCA see the signal? And indeed, what we'll show is that there is a critical value, beta critical, such that if beta is bigger than beta critical, there is a popping out, an eigenvalue shows up, pops out of the support, pops out of what we call this popping out of the bulk, right? Bulk would be the bulk of this distribution, pops out of the bulk. If beta smaller than beta critical, it doesn't. Nothing happens, right? Nothing happens. In the sense that it looks just as if there was no signal. Okay, and the question is, can we understand this? Okay, and so what I'm going to do now is I'm going to do a semi-rigorous, okay, not fully rigorous derivation of beta c. Okay, even though this is not fully rigorous, it can be made rigorous, right? It can be made rigorous. This is important, right? So it's not like I'm just giving some kind of heuristic. It can be made rigorous. It's just that I'm going to skip a few steps to make it, because the technical steps are kind of, they're laborious and they take time and a lot of effort. I want to talk about other things too, but it can be made rigorous, and there's a reference in the notes, right? A reference in the notes. Okay. So we're going to work out what is the right of beta c, and I'm going to, every time I do something that's not quite rigorous, I'll mention it, but the steps can indeed be made rigorous. Okay, so we're going to try to understand the behavior. So the goal is to understand, right? Goal is to understand behavior of eigenvalues of this sample covariance matrix, Sn equal 1 over n sum I 1 to n of xi transpose, right, where all the xi's are equal to, they're drawn from n0, beta identity plus beta u transpose. Okay. So we start by noting that the points xi, right, they can be written as identity plus beta u transpose square root times zi, right? Where zi's now are just standard Gaussians, right? Because what we know from the theorem of Mashenko-Pastore, what is the distribution of the covariance of just Gaussian, standard Gaussian vectors, right? So we're going to sort of try to reduce to that case. Okay, so what does that mean? This means in particular that, I can write Sn, right, to be just 1 over n. Okay, so let's write it out. I from 1 to n, right? Identity plus beta u transpose. Zi transpose. Okay, identity beta u plus. Okay, and this matrix is symmetric, so I don't have to take another transpose. Okay. All right, so if I now write Zn is equal to 1 over n sum I from 1 to n of Zi transpose, right? This matrix, I know its eigenvalues, right? This means I can write Sn equal to, right, just identity plus beta u transpose. Okay, 1/2 Cn. Right, so we want to know how this affects the eigenvalues of Zn, right? That's going to be the strategy. Okay, so now, now a few tricks, right? And for now everything is okay. In the middle, I'll do a few tricks. I won't justify completely, but I'll give references where those steps can be justified, are justified properly. Okay, so first of all, Sn and the matrix Zn times identity plus beta u transpose are similar. Right, similar in the sense of linear algebra, right? I can multiply by I plus beta u transpose to the minus 1/2 on the left, and by the inverse of that on the right, and I get exactly this matrix. So they have, right? So they have the same eigenvalues. So now this means I can study this this matrix instead. Okay. Now this matrix, this one is a rank 1 perturbation, right? Is a rank 1 perturbation of Zn, right? Indeed, I mean, what is this matrix equal to? This matrix equal to Zn plus Zn beta u transpose, right? Which clearly is a rank 1 matrix. Okay, so we even know we have these interlacing theorems of eigenvalues and so on. We expect the spectrum doesn't change very much, right? But what we expect is that there was one eigenvalue, the one towards the right, that might be far away, at least when beta is big, as it's exactly what we want to predict. Right, and moreover, the eigenvalues of Zn, we know that they'll satisfy this Mashenko-Pastur distribution, right? So this is what we're going to use. Okay, so let lambda be the largest eigenvalue of Sn. Right, and sort of what we hope is that it's something that it's an eigenvalue of Sn and not of Zn, right? Because we hope that it's, the eigenvalue that pops out of the support, right? The picture we have in mind is that these were the eigenvalues of Zn, and we're looking at Sn as now another eigenvalue, right? So it's sort of the eigenvalue of Sn that is not in the bulk of the spectrum of Zn, okay? That's the intuition. Okay, so now if we do this, what does this mean? Let V be the associated eigenvector. It means that Zn, right? I mean, V is not the eigenvector of Sn, it's the eigenvector of this similar matrix. V equals lambda V. Okay, so we expect to have this equation. Okay, so far so good. So now let's subtract, let's take minus Zn on both sides, Znv, sorry, on both sides. Both sides. Okay, so what do we get? Right, it's equivalent to, right, this goes away, I get Zn beta u transpose V equals, right, lambda identity minus Zn. I mean, for those of you that have seen some random matrix, you might recognize things like the resolvent and Stieltjes transforms and things like this. I mean, this is one way of trying to make this rigorous, but it's sort of outside the scope of this course, so I'm not going to go into that here. Okay, and now again, let's assume that lambda is not like assume, right? And again, this can be made precise. So it's not an eigenvalue of Zn. Right, this means that lambda I minus Zn is invertible. So if we have this, okay, so this is like sort of warning. I mean, this is not rigorous what I'm doing, but it can be argued rigorously. But if we do that, then we get that lambda I minus Zn inverse Zn, right, beta u U transpose V equals V. Right, and indeed here we're sort of using already the fact that lambda is an eigenvalue that's, outside of the bulk, right? Otherwise we'd run into problems here. But okay, let's just assume it's not an eigenvalue of Zn and see what calculations we get. Right? We immediately are getting here too that, immediately we're getting that U transpose V needs to be non-zero, right? Otherwise, V would be 0, right? Because the left-hand side would be 0, right? Because there's the U transpose V here. Okay, so in a way, we're assuming that U transpose V is non-zero. Okay, so now let's multiply by U on, let's multiply by U transpose on both sides. So what do we have? We get that U transpose lambda identity minus Zn minus 1 Zn beta U transpose V equals U transpose V. Again, because U transpose V is not 0, right, I can divide by U transpose V on both sides. Okay. What do I get? I get that U transpose lambda identity minus Zn minus 1 Zn U is equal to 1 over beta. Okay, so now, if U is an eigenvalue, an eigenvector of Zn, right? If U is an eigenvector of Zn, then I would be able to write this, right? Because, U times Zn would be like the associated lambda times U, and then here it would also be an eigenvector of this. It would just be lambda minus the eigenvalue. So what we're going to do is we're going to write U as we're going to take W1 through WP, the eigenvectors of Zn, right? They form an orthonormal basis. And we're going to write U equals summa alpha I Wi, right? We're going to write U in this basis. Okay, so we write U in this basis because once we do that, we know exactly what this is like, right? Because now it's very easy to write this expression in the left, right? Because we just have to write a sum, right? We just have to write a sum here and a sum here, right? And the Wi's, they carry through because Wi is an eigenvector of Zn, so it's still Wi. The eigenvectors of Zn and, Zn inverse are the same, and lambda I minus Z inverse, they're also the same. So, this, if I have here Wi, this is still a multiple of Wi, and so it'll be orthogonal to any other Wj's, only the sort of the terms I with I survive. So this is equal to the sum from I from 1 to P, right, of, I get Wi times Zn will give me lambda I Wi. Okay, so let's give a definition. So lambda 1, so I need to write what eigenvalues are. Right, Zn Wi is equal to lambda I Wi. Okay, so what do I get? Once I take the Wi, I get lambda I Wi, right? And then the eigenvalue here is 1 over lambda minus lambda I. I get the Wi, I get that times lambda y, and then when I multiply it by Wi, it gives me 1. So really what do I have? Right? I have the alpha I squared, and then I get lambda I over lambda minus lambda I. Okay, and I get that this is 1 over beta. Okay. Now, because, right, the Zn, the distribution of Zn and the U, they're independent, right? I picked U and then I draw, there should be no relations between U and the Zn. The Zn are the isotropic Gaussian vectors. And so it's reasonable to expect, like, what you would expect, right? Because the norm of U squared is 1, right? You would expect that, the Wi's are all orthogonal, so you expect the typical behavior of an alpha I square, right? In general, this expectation would be 1 over P, right? So then when I take the norm, we get, right, when I take the norm on the right-hand side here, I get the norm being 1. So let's assume, again, and this can be made, again, rigorous via concentration, that alpha I squared is exactly equal to 1 over P, okay, for our calculation. So let's do that. So once we do that, what do we have? Right, we just have 1 over P, sum I from 1 to P of lambda I over lambda minus lambda I equals 1 over beta. Okay, but now we know, right? We know that the eigenvalues of Zn are converging to this Mashenko-Pastur. So lambda 1, all the way to lambda P, they should behave, right? They should be distributed essentially like the Mashenko-Pasteur distribution, right, of this parameter gamma. Okay, so what this means in the limit, right, as p goes to infinity and then goes to infinity and so on, what we expect is that this sum is well approximated by the integral, right? This is just an expected value of, right? We expect this to be the same thing. It's just the expected value under the Mashenko-Pasteur distribution of gamma of, t. So where lambda I is drawn this way, or let me use another variable, t is drawn according to this, t lambda minus t, right? And then this is 1 over beta. Now this we can compute, right? Because this is just the integral from the bottom of the Mashenko-Pasteur to the top, right? Of t lambda minus t dt, df gamma t, right, equals 1 over beta. Okay, now we have this complicated integral, right? Now we can use, but we know we had it from before, right? It's given by the integral over here, right? It's this integral over here, right? We just have to compute this integral. Okay, so you put it in some, either you look at an integral table or you put it in some software to compute integrals. Okay, and when you do this, you get the following: that this integral is equal to 1 over 4 gamma 2 lambda minus gamma minus plus gamma plus gamma minus gamma plus. Right? Remember that we're sort of assuming that lambda is outside of the support, right? So it'll be bigger than gamma minus gamma plus. Right? This is equal to 1 over beta. Okay, so how would we look at critical beta, right? A good place to look at the critical beta is to try to ask when is it in this formula, when is it that gamma will look like, that lambda will look like gamma plus, right? Because this would be the critical place at which this argument stops working. Okay, so let's work it out. So when you do that, what do we get? We get that, 1 over beta here is equal to, and what we get from here, we get 1. Okay, let's do it. We get 1 over 4 gamma. Okay, and now we get 2 lambda plus minus lambda plus minus 2, gamma plus lambda minus, it's gamma plus minus gamma plus. Okay, so let's compute this. So what is this equal to, right? Okay, this term goes away because, right, this is 0, so this thing is 0. So what do we get? We get 1 over 4 gamma, right? And now I get a gamma plus minus gamma minus, right? Because this cancels with one of them. So basically I get a gamma plus minus gamma minus. Okay, but what is this equal to? Right? So we saw what gamma plus and gamma minus are. So this is 1 plus root gamma squared plus minus, 1 minus root gamma minus squared over 4 gamma. Okay, so let's work this out. Okay, the square terms all cancel out, so all that survives is, 2 square root gamma and then 2 square root gamma from here, so 4 square root gamma over 4 gamma, so we get 1 over square root gamma. Right, so then the beta critical, at this calculation, which, there was many things that weren't rigorous, but all this can be made rigorous, is equal to root gamma. Okay. And indeed, this is square root p over n. Right? In particular, it is a lot smaller, right? It is a lot smaller than the place where you would expect things would happen because it's bigger than what the spectrum of the noise. Right, and the theorem actually looks the following. Right, so if the maximum eigenvalue of Sn, okay, will go to, as p and n goes to infinity, will go to beta plus 1. Right, 1 plus gamma over beta, right? If beta is bigger or equal than this beta critical, right? And when it's beta critical, you'll see this will give the same thing as below. And nothing will happen if beta is smaller or equal than beta critical. And we sort of proved this. I mean, we didn't really prove it. We derived the beta c sort of an unrigorous way, but our derivation can be made rigorous, right? And this is known as the BBP transition. After Baike, Benarus, and PCA, this is known as the BBP transition. Right? So we can compute the critical place at which we see eigenvalues coming out of the support. And then, of course, the natural question is to ask, okay, but does this actually mean that the eigenvector has some meaning? And indeed it does. So you can also prove, I mean, essentially by running the same kind of non-rigorous calculation, you can actually derive this as well. Right? That Vmax, correlates with U. Okay, and the correlation goes to the following. So it's 0 if beta is smaller than beta c, and if beta is bigger than, square root gamma, right, which is beta c. Okay, I should say beta critical is root gamma. Use here root gamma because it'll be easier to see the expression. Right, 1 minus gamma over beta squared, 1 plus gamma over beta squared, right? And if beta is equal to root gamma, this becomes, on the top, this becomes 0 as well, right? So it matches. Okay, and so this is the so-called BBP transition. There's lots and lots of super interesting extensions and open problems related to this. And so just before we finish with this chapter, let me just mention very quickly that there's other random matrices, and some of them will make an appearance later. So in particular, one important random matrix is the Vignette Matrix. Right. So the Vignette Matrix is the following. You take a matrix W, symmetric, essentially with independent entries. So Wij, is just n01, right? With it needs to be symmetric, so we can do this for, say, I bigger than j. Okay, all independent. And Wii, not that it's very important, but tends to be a variance 2, okay, just to make the matrix rotation invariant. Okay, so this is a matrix with all independent entries, right? So it's a bit different than taking this X itself had independent entries, but if we took XX transpose, so it's a bit of a different thing. And so now 1 over root n W, right, is sort of the right normalization for the Vignette matrix. It's not so surprising, right? Because before we had XX transpose, we didn't divide it by n. Here we only have one of them. Okay, the limit of the eigenvalues, so the eigenvalues, will go to the so-called semicircular law. Right? And the semicircular law is given, I'll write here the expression, is given by 1 over 2 pi, square root of 4 minus x squared, and, multiplied by the, only between minus 2 and 2, right? So, okay, but this is this beautiful, you should try it on the computer. Just draw a matrix. Even with that n be like 40, you already see for sure even less. Okay, and now plot the histogram of the eigenvalues, and you'll see this beautiful semicircular law. You'll see that the eigenvalues basically completely satisfying this, converging very quickly to the semicircular law. And again, you can ask all sorts of the same questions, right? You can take V, a vector of norm 1, then the natural thing to ask there is to take the matrix, take the matrix Y equals, say, 1 over root n W plus, some C times VV transpose, and ask for which values of C do you see something here popping out of the support. And so this is well understood. Okay, and you can do it with very, very similar techniques. Basically, the value here, even though the largest eigenvalue is at 2, the BBP transition here happens when Xi is 1. So when Xi is smaller or equal than 1, nothing happens. So the lambda max, lambda max of y will go to 2, as n goes to infinity. If gamma is bigger than 1, then lambda max gamma goes to Xi plus 1 over Xi. Okay, so now just a few quick comments. You can get some correlation of the leading eigenvector exactly the same way and so on. You can look at all of this in the lecture notes. So just before we finish, just a few comments, right? One is that there's something else that we're a little sloppy about, which is that just because the distribution of, say, in this sense of the semicircular law, the same thing for the Mashenko-Pastor, it doesn't guarantee that there's no already eigenvalue somewhere on the top, right? Because it could be that you get weak convergence that most eigenvalues are like here, the measure of the eigenvalues, but one of them in the limit will have measure 0, so it wouldn't matter. So it could be that there is one eigenvalue already far away, and sort of then this stuff wouldn't even make much sense. But one can prove that indeed there is no eigenvalue. When there is no perturbation, there is no eigenvalue that ever runs out of the support of the semicircular law or the Mashenko-Pastor law in the case of covariance matrices. Okay, so that's important to notice.